You can solve for other variables in the future value annuity formula, and one of the problems I'd like to show you is how to solve a time problem in a future value annuity. So let's take a look at number 5 here. How long will it take for monthly payments of $500 to have a future value of $100,000 if money earns 6% compounded monthly? Now you can actually answer this question sorta. Well, when I say answer, I don't mean you would get the correct answer, but you can get an estimation by simply dividing 500 into 100,000. And basically, if you divide 500 into 100,000, you'll get 200. But what that means is if you weren't earning any interest, then it would take you 200 payments or 200 months for this to happen. But obviously you're earning 6% interest, so it shouldn't take 200 months. So, but to see how long, but at least the 200 kind of gives us an idea of what the answer should be less than, because if we get an answer more than 200, we know we did something wrong. So anyway, let's take a look at how we would handle this problem. Now, we know it is a future value annuity because two things. Number one, we're making monthly payments, so it's an annuity, and these payments will increase our balance, so therefore it's a future value annuity. So go back and look at the future value annuity formula. Remember, it's future value equals payment times 1 plus I to the n minus 1 all over I. Now, we know the future value is 100,000. We know the payment is 500. We know I would be the annual rate, 0.06 divided by 12, since it's monthly. And then n is the unknown because we're trying to solve for time. So when we get the answer for n, that'll give us the number of months. And then don't forget the minus 1, and then in the denominator you have the I in the denominator as well. Now, to solve this, what you're going to want to do is you're going to want to figure out a way to isolate this expression, because if you can isolate this expression, then you can use logs to solve for n. So the first thing I'm going to do is I'm going to go ahead and write 0.06 over 12 as 0.005. So I did that. And then also in this step, I'm going to divide both sides by 500. So just take this and divide it by 500 to cancel the 500. And then take this and divide it by 500, and that will give you 200. And so notice down here, I got 200 over here, and then of course on the right hand side the 500 is now gone. Now the next thing I want to do is I want to get rid of this denominator 0.005, and the way to get rid of a denominator is just multiply both sides of this equation by 0.005. Now, so if I multiply the right-hand side by 0.005, it'll just cancel the 0.005. And then if you multiply the left-hand side by 0.005, 200 times 0.005 is just 1. Now, I'm getting close. I have this 1 plus 0.005 to the n minus 1. So I want to isolate the 1 plus 0.005 to the n. Let's go ahead and add the 1 and the 0.005. So what I want to isolate is the 1.005 to the n. Now to get rid of this minus 1, simply add 1 to both sides. And so if I add 1 to this side, of course it'll cancel it. And then if I add 1 to the left, I'll get 2. So now I have my 1.005 to the n isolated. And so to solve for n, just take the natural log of both sides. And so if I take the natural log of the left, I get natural log of 2. And if I take the natural log of the right, I get natural log of 1.005 to the n. And you'll remember with your log properties, you can actually write that as n times the natural log of 1.005. So now you have a number on the left, natural log of 2, equals to n times the number on the right, natural log of 1.005. So to solve for n, just divide the natural log of 1.005 into both sides, and of course if you divide it on the right hand side you'll just get n, and if you divide it on the left hand side you'll get natural log of 2 divided by natural log of 1.005, And this actually comes out, I think, to 138 point something, but remember, we always round these up to the next higher integer, so the answer would be 139, and since n represents months, that would be 139 months. So remember, it should be less than 200, and of course it is less than 200. So n is equal to 139 months. When you try to solve for R or I, either the annual rate or the periodic rate in an ordinary annuity, there's really no nice algebraic way to isolate the variable. So what we're going to do here is I'm going to show you how to solve this by looking at the graph. So let me just start with an example. It says Mr. Ray has deposited $150 per month into an ordinary annuity. After 14 years, the annuity is worth $90,000. What annual rate, compounded monthly, has this annuity earned during the 14 year? Now, the fact that it's compounded monthly will affect our final answer. So let's just remember this, that we want the annual rate, but remember it's compounded monthly. Okay, so let me show you how we can do this. First of all, since we have $150 per month into the investment, we know it's an annuity, and the $150 will increase the balance. So we're dealing with a future value annuity. Now you can solve this for I and or R, but what I prefer to do is just to solve it for I so that the formula is simplified. So I'm going to solve it for I. Let's take a look at the formula. Here's the formula for the future value of an annuity. Now we know that the future value is $90,000, and we know that the payment is $150. Now we don't know I, but we do know N because this is for 14 years monthly, so 14 times 12 is 168. So we know N is 168. Now, what I'm going to do next is I'm going to go ahead and divide both sides by 150. And if I divide 90,000 by 150, you get 600. Now, if you read below, you'll see that you actually can solve it with these two formulas, or these two functions, but I'm going to go ahead and divide the 150 into 90,000 and get 600. Now, what I'm going to do is I'm actually going to go to a graphing utility, and I'm going to graph the function y equals 600 and also graph this function. Notice I changed I to x because most graphing utilities like to use the variable x, but you may not have to, but I'm going to change I to x here. Now, so what I'm going to do is I'm going to graph y equals 600 and y equal this function on the same graph. Now, when I do that, this is what it's going to look like. This is a close-up view. Now, a couple things you need to know. In order to be able to see the graph of y equals 600, which is the red line here, you have to have your y window containing 600. So I used a y window like 500 to 700, so it would contain 600. And then also, so that you can contain this rate or see this rate better, I went ahead and let the X window be a very small window. So I'm only going to like 0 over to 0.3. So because that rate is a very small number. But anyway, if you graph y equals 600 and you also graph this function, you'll see that the two functions intersect right here where x is 0.01305. So now that tells me that I is 0.01305 or 1.305%, but that's the monthly rate. Now if I want the annual rate, I actually have to multiply this by 12 to get the annual rate. So multiply 12 by 1.305% and I get 15.66%. So the monthly rate's 1.305% and the annual rate is 15.66%. You can also do this by trial and error, but it's a little bit cumbersome to do that. So You know, that's why I like to use the graphing utility. Okay, let's wrap this video up by looking at this problem, number 7. Basically, let me just summarize here. Michael is a baby boomer, and he's decided that he's going to deposit $200 each month into an account that pays 7.2% annual rate, compounded monthly for 20 years. So the first thing we're going to look at is how much money will be in the account at the end of 20 years. Okay, I don't want to spend a lot of time on that because that's pretty straightforward. We know this is a future value annuity, so just use the future value annuity formula. Put in 200 for the payment, put in 0.072 for R, put in 12 for M, put in 240 for N. Since it's 20 years, that'd be 240 periods. And then just do it on the calculator and you get $106,752 and change. Now part B says suppose Michael determined he actually needs $130,000. Well, if he needs $130,000, then he's going to need more than what he's got here. So one way to increase that is to change the rate. So let's see what rate he would need to achieve this goal. So what we're going to do now is use the same formula, but we're going to plug in $130,000 for the future value, and we're going to leave the rate unknown. Now notice I left this as R. Now if you want to, you can go ahead and just call this, instead of R over 12, you can call this I if you want to. But basically I either need to solve for I and then multiply it by 12 or solve for R. So put in 200 for the payment, put in I or R over 12 here, and here, and then put 240 in for N. And then you can solve this like I did before. You can divide both sides by 200, and then you can graph the left-hand side and graph the right-hand side, and then find where the two graphs intersect. And I got 8.78% to the nearest decimal. Okay, now another way that he could increase his future value is to change the payment amount. So let's assume that he can't get the higher rate. So let's assume that the rate has to stay at 7.2%, and then let's solve this as a sinking fund and find out what he would have to change his payment to in order to get $130,000. So as a sinking fund, I would use the payment formula, and I'd put $130,000 in for the future value, and then leave the rate as 0.072 divided by 12, and of course leave N as 240, and you'll see that now he would have to deposit $243.55 each month. Okay, now the last way that we could consider him to get the $130,000 is, okay, let's leave the payment at $200 a month, let's leave the rate at 7.2%, but let's increase the time. So we can go back to our future value formula and put in the $130,000 for future value, put in $200 for the payment, leave the rate as 7.2% divided by 12, and then N would be the unknown. Now I showed you earlier how to solve for N, and you can do that yourself. You can, divide both sides by 200, then multiply both sides by the 0.07 over 2 over 12, and then add 1 to both sides, then take logs, and that will help you solve that. So there N would be 266 months. So there's 3 ways that he can increase his future value to $130,000. He could increase the rate, or he could increase the amount of the payments, or he could increase the length or the number of payments that he makes. There is one other problem down here, but I think you can follow that one pretty well. To answer the second question, all I did was I found the future value for 1 year, and then I subtracted the amount of the payments made for 1 year to get the total interest earned in that 1 year. So if you need to, just pause the video and read number 8 on your own. And that completes the section on future value annuities. And in the next section, we'll talk about present value annuities.